Happy Monday morning, everybody. I hope everybody's doing well. Squeaky microphone stand here. Sorry about that. I should probably fix this. 100% sure why that's so squeaky. Anyway, I hope everybody had a good weekend. Happy Monday morning, like I said. Yeah, so we have just finished. I actually did not. I deleted all my previous notes. So let me just hop over to this and showcase what we've kind of just finished. So we just finished going through a lot of different kinds of tests, right, for divergence and convergence of series. So given a series, really, in my opinion, probably the best first move is to check the divergence test, right? Just check the limit as n goes to infinity of the sequence. If that is non-zero, then the series will diverge. Very, very fast, easy, very nice. The next easiest test really, it just depends on the look of your given series. If your series, excuse me, looks geometric, that is, it is something of the form summation something to the nth power. If that's the case, then it's not really called a geometric series test, but you get the idea. It's a geometric series, and so you could test it to see if it converges or diverges. It will converge if the common ratio argument here is less than 1 in magnitude. That's when it will converge, and it will diverge if it's greater than or equal to 1 in magnitude. So that's kind of my second go-to. It's pretty obvious when you have a geometric series. That's why it's my second go-to as far as testing for convergence or divergence. When I write these out in the lecture notes, I don't put them in the order necessarily that I tackle my convergence or divergence tactics. It's just listen the way we learn them. To be honest with you, I save the integral test to the last. Usually the integral test is not my favorite test to use, and so I kind of hold off on that. The P-series test is also incredibly rare to be able to use. You use it when usually within another proof. So maybe you're using the series comparison test and you compare it to your series to a 1 over n to the third power or something like that. If that were the case, then you were using a subtest or a secondary test called a P-series test. So anyhow, so the integral test and P-series test are kind of rare for me to reach for. We have recently been introduced to two comparison tests, the series and limit comparison tests. And of those two, they both are very useful, actually. And at times, the limit comparison test cannot be used, and therefore you have to kind of switch over to the series comparison test. Between the two of these, I much prefer the limit comparison test just because I don't have to establish an order for my sequences that my series are based upon. So in other words, with the limit comparison test, I just need my sequence terms to be positive or at least non-negative. And then I can use the limit comparison test. Remember, the limit comparison test just says you take the ratio of the sequence that you've been handed for your series, and you compare that to, or you build a ratio of that against a completely different sequence or somewhat related sequence that you know the convergence or the divergence for its related series. That sounds very confusing, but that's just the only way really to say it. If that limit of that ratio is some positive constant, and it can't be 0, it has to actually be a positive constant, then the series, oh yeah, it's over here. Then the series A sub n, I'm waiting for it, my screen to catch up. There we go. The series A sub n and B sub n will converge or diverge together. So that's a really nice test to use. However, Sometimes you can't use it, and so you have to use the series comparison test. The problem with the series comparison test, again, is that you have to not only build this extra sequence, but you have to have an order. So when you're comparing, you have to basically find a sequence that's either greater than or equal to your given sequence, or strictly or less than or equal to your given sequence. Um, Divergence below of the series implies divergence above for the series. Convergence above for the series implies convergence below for the series. So that's kind of a reminder of some of the tests we've gone through so far. I'm not going to scroll down because that contains a new test. So I'm going to go ahead and scroll back up. But that's where we've built up to this point. We finally enter into our last test, or our last two tests, which are the ratio and root tests. And to be very honest with you, uh, these end up being used about 80% of the time. So you use these quite a bit. There are some restrictions on using them, but not very much, actually. And when you get a series that converges by either of these tests, it's a very special type of convergence. It's called absolute convergence. So let's go ahead and start by talking about what absolute convergence really is. So let's go ahead and zoom in here. So note, this is actually the first test for the convergence of a series with terms that are not always positive, but are not necessarily alternating in a pattern. So we do have actually two tests previously for series that have negative terms. So maybe I should write that down off to the side so that I remind you of them. Aside, and my ink will be slightly behind me, not very much though. We have two tests so far for series with, or maybe I should not say with, I'll say containing, because that's the implication there is a little bit better. Containing negative terms. So let's think about those tests. The limit comparison and series comparison tests require that our terms be positive. So it's not going to be either of those. The integral test actually requires that our terms eventually be just positive. So again, it's not going to be the integral test. However, geometric series those actually can have negative terms, right? You could have a summation n equals 0 to infinity of -1, not -1, sorry, of, let's say, a -2/3 to the nth power. That will converge because the common ratio, -2/3, in absolute value is less than 1. So this converges because the absolute value of -2/3, not 3/2, but 2/3 is less than 1. So this is a series that does contain negative terms. They're alternating negative terms, actually. So the terms pop back and forth every other term through positive and negative. The other type of test we can use for series that have negative terms is the alternating series test. And an alternating series is a very special kind of series. It doesn't necessarily have to be geometric. It could be something like the following: the summation n equals 0 to infinity of a -1 to the nth over n squared plus 18, or something like that. That series, the terms are actually alternating. So when n is equal to 0, I get 1 over 18. And when n is equal to 1, I get -1 over 19 and plus 1 over 22 minus ... right? You go on forever. But that will pop back and forth between positive and negative. So the only two tests we have that can have negative terms in their series are the geometric series, quote unquote, test, even though it's technically not a test, and the alternating series test. But they require every other term to pop back and forth between positive and negative. However, we don't have any test for series where the terms don't necessarily pop back and forth every other term, but instead for series of this form, like let's just say we have something like 1 minus 1/2 minus 1/3 plus 1/4 minus 1/5 minus 1/6 plus 1/7 plus 1/8, right? Minus dot dot dot. There's no real pattern to the plus minus business here. And because of that, it's not popping back and forth. We don't have anything for this. So we don't have a test for this. Okay. So we need to build a test. And that's what the ratio and root tests are for. So that's just giving you a heads up as to what today is all about, is what do we do if we have a series that's not necessarily popping back and forth between terms, but might have no pattern to the positive and negativity of the terms. Also, the tests we developed today are useful for any series, whether it pops back and forth between positive and negative, or all the terms are positive, or all the terms are negative. The tests we're going to develop there's two tests. The tests we're going to develop are for two very powerful, or they are for any series, and they're very powerful tests. That's how I want to say it. So let's talk about absolute convergence before we get there. A series is said to be absolutely convergent if the sum of the absolute values. Oh, I said the word series, so my phone is now starting to talk to me. All right. If the sum of the absolute value of the terms of the series converges. So in other words, if you're handed a series that contains some negative terms in it, it is said to be absolutely convergent if, when you just add up everything and force every term to be positive, if it still converges, then we would say this series is absolutely convergent. Okay. And I'm just kind of prepping something off to the side here, so give me a moment. Yeah, perfect. And let's see. If I have to wait for my screen to catch up. If the series A sub n converges, so if the original series converges, but the summation of its absolute value of its terms does not converge, then we say the series is conditionally convergent because the original series converges, but its absolute values, the sum of its absolute values, do not. So a very, well, do I have one offhand that I can? Yeah. Okay. For example, the summation of -1 to the nth over n. That's the alternating harmonic series. We know that the alternating harmonic series, I have to start at 1 here. The alternating harmonic series we know is going to be convergent. We've actually proven that in when we were in alternating series test. That was like one of our first examples. So we know this series converges. But the series of from n equals 1 to infinity of the absolute value of the terms of that sequence, well, that would be the series from n equals 1 to infinity of 1 over n. And we know that diverges because that's the harmonic series. So that diverges. It's the harmonic series. And that was the first series that we proved diverge. So notice that our original blue series converges, but when you sum up the absolute value of its terms, that series will diverge. Thus, we would normally say, so just a new phrasing, that's all. We would normally say the original series 1 to infinity of -1 to the nth over n, we happen to know that converges, but because it's the absolute values of its terms, when we add those up, they don't converge. We would then say this is conditionally convergent. That tells the world, as written, it converges. But the sum of its absolute values totally does not. And you might be wondering, well, why does that matter? Like, is that super duper important? It actually is. There's a very, very obscure theorem that comes into play when you have a series that is conditionally convergent versus a series that's absolutely convergent. In fact, I should showcase a series that's absolutely convergent just so that we can have that out right now. So let's go ahead and break the board here and create a separate example. So let's look at the summation n equals 1 to infinity of a -1 to the nth over n squared. We'll just keep it like that. -1 to the nth over n squared. That's just a simple one. Okay. First of all, that series, it's an alternating series. Remember, to use the alternating series test, we need b sub n, the non-negative part of that. We need that sequence to be decreasing, and we need it to tend to 0. Well, we happen to know the limit as n goes to infinity of 1 over n squared definitely is 0. And we happen to know that I'm just going to, well, I'll go ahead and prove it. If f of x is equal to 1 over x squared, then f prime of x is equal to a -1 over x cubed, which is negative if x is positive. So that tells us that b sub n is decreasing. Now remember, the alternating series test says if you have an alternating series, and if the positive version of your sequence, so 1 over n squared, if that tends to 0, check, and if it's decreasing, check, then the series will converge. So I'm just going to say this converges by the alternating series test. Now the question is, what about its absolute value? Did I do negative? Oh, I did. Sorry about that. -2 over x cubed. Thank you. I was just kind of barreling through. Well, I got up at 4 a.m. What am I going to say? All right. So it converges by the alternating series test. Now let's take a look at its absolute value. Notice the ink I'm using. Green means good. So, and the summation n equals 1 to infinity of the absolute value of this is equal to the summation. I joke every once in a while because some instructors will make a mistake and they're like, oh, yeah. I was just testing to make sure you're watching. No, I innocently made that dumb mistake. Sorry about that. Let's see. The summation of the absolute values of the terms, well, that's a summation of 1 over n squared. And we know that converges by the p-series test. One of the rare instances where I can actually use the p-series test. So converges by p-series test. So look, not only does our alternating series converge, but the summation of its absolute value, that converges as well. If you combine those two arguments, that tells me that our original series, if I'm talking to somebody or if I'm working in an industry or something like that, and I have to work in engineering and I have some series that's alternating and I have to discuss this with somebody and say, well, okay, I happen to know the series we've created here. This is absolutely convergent. because not only is the original series convergent, but its summation of its absolute values also converges. So when I say is absolutely convergent, that conveys all of that information, that not only does this alternating series converge, but its absolute values converge as well. All right. So I hope that I haven't made any proofs. It's just a definition, but I hope that makes sense. The distinction between conditionally convergent and absolutely convergent. Conditionally convergent is when the series that you're handed converges, but the sum of its absolute values does not. And absolute convergence is when the series you've been handed converges, and so does the sum of its absolute values of its terms. All right. But there is a cool theorem, because if I just told you this definition and walked away, that would give us no reason to use it. Mainly because if there's no impact from having an absolutely convergent series, there's no need to talk about it. There's absolutely no need to talk about something if there's no implication, right? It's unimportant if there's nothing gained from having a series that's absolutely convergent. So what is gained by having a series that's absolutely convergent? Well, here's a theorem. I try to succinctly state this, that absolute convergence implies convergence. So if I have a series and somebody says, oh, this series absolutely converges, then I know the series converges. Not only is the sum of its absolute values convergent, but the series itself is convergent. So that's a big umbrella phrase. If I tell you a series is absolutely convergent, not only is the summation of its absolute values convergent, but the series itself has to be convergent. The proof is pretty neat and pretty simple, so we're going to go ahead and do it. So let's go ahead and say this. So let's going to say note. Well, first of all, I'll go ahead and assume. Suppose. SPS to me means suppose. Suppose that the summation A sub n is absolutely convergent. So that's the antecedent. We're supposing the if part. Right? We're allowed to do that. That's how you do any proof in mathematics usually, unless you're doing a proof by contradiction or mathematical induction. So let's suppose that our series is absolutely convergent. Now, that basically means that the summation of its absolute values, so I'll just write the consequence of it, that the summation of the absolute values of our series terms is convergent. Now, right now, we cannot assume, because we're trying to prove that the series itself, we want to prove the series itself is convergent. But right now, by definition, all I have is that the series of the absolute values is convergent. We're going to go ahead and prove that the series, therefore, must be convergent. So how do we get that? We're going to note 0 is definitely less than or equal to A sub n plus the absolute value of A sub n. I hope that makes sense. Think about if you have a term that's, for example, -3. Let's just say that's A sub n. Well, then if you add to that the absolute value of that term, it becomes 0. So that should make sense, right? Also, if the term is not negative and you add to it the absolute value of it, well, it's still greater than or equal to 0. So I hope that makes sense, that A sub n, any random term in the summation of our original series, plus the absolute value of that term, it's got to be non-negative. Okay. Also, it's going to be less than or equal to twice the absolute value of that term. Again, think about it. If A sub n were -3, and therefore the absolute value of A sub n is the absolute value of -3, you add those two up, -3 plus 3, it's 0. That's definitely between 0 and twice the absolute value of a -3, which is 6. On the other hand, if your term was positive 3, well, 3 plus the absolute value of 3 is 6, and that's less than or equal to twice the absolute value of 3, or 6. So this inequality should be okay. You should be all right with that statement. Okay. But we know, or we have assumed, that the summation of the absolute value converges. Remember what we're trying to show. We're trying to show that the summation of a sub n is convergent. Okay. Therefore, the summation, I'll write it this way, of twice the absolute value. Well, that's just twice a constant, right? If I tell you the summation of the absolute value of the terms converges, it converges to find some finite number. Well, then the summation of twice the absolute value is just twice that finite number. And so that will also converge. Now, this alone does not finish the proof. We have a little bit of extra work we need to do here. So I'm going to go ahead and say it this way. Hence, the summation a sub n can be written as the summation of a sub n plus the absolute value of a sub n minus the absolute value of a sub n. And actually, I don't know if I actually need that twice a sub n in there. Oh, no, I don't. I could just do a series comparison test, right? So if I happen to know that this converges, then I know this converges, right? So if by the series comparison test, the summation a sub n plus absolute value of a sub n converges. That's by the series comparison test. We just happen to have a sequence bounding our sequence above, and that the summation of that sequence converges. So therefore, this summation of this sequence must converge. But that doesn't tell us that a sub n converges, right? However, we could write a sub n in a very, or the series of a sub n in a very special way. The series of a sub n is equal to, the series of a sub n plus the absolute value of a sub n minus the absolute value of a sub n, which is equal to the series of a sub n plus the absolute value of a sub n minus the series of the absolute value of a sub n. And remember, actually, I'll just say it this way. Remember, this converges. We've just showed that by the series comparison test. And this converges because that's our assumption. So it's a finite number minus a finite number. That implies the original series must converge. It's actually a very nice proof. I like it a lot. Very clean proof. So again, absolute convergence implies regular old convergence. So that's great. So if somebody, from this point forward, if somebody hands me a series that has some negative terms, I have the option to look at the absolute value, the summation of the absolute value of the sequence, rather than the alternating bit. I can just say, well, let me just check to see if I just added up the absolute values of those terms, if that converges. Because if it does, then the series you handed me has to converge. If I get absolute convergence, then I get convergence. Summation absolute a sub n implies converges, sorry. implies summation A sub n converges. That's really a very, very cool use of absolute convergence. So this allows us to then engage with all of our previous tests if we are handed a series that has like some alternating terms in it or some negative terms that pop up every once in a while. We could just say, you know what, those negative terms are very frustrating and annoying, so let's go ahead and just deal with only adding up the absolute values and see if that converges. If it does, then we know the original series must converge by this theorem. And that's a great tactic. Now, let me just look at my notes here. Yeah. The next thing I'm going to state is a weirdness. It's not something that you're going to have to deal with, but I just think theoretically it's one of the most interesting parts of this course. It's kind of like, remember when we did the Gabriel's horn, that we found that the area underneath y equals 1 over x was infinite. All this area was infinite. Yet when you rotate it around and create a three-dimensional object, the volume was finite. Remember that? That was a really cool kind of theoretically interesting topic. Well, what we're about to see is also incredibly interesting. I've written it out in language so that it's a little bit easier to understand. So there's a very interesting and often confounding theorem introduced in this section. And actually, it's not really a theorem the author spends any time on. He just mentions it in a paragraph, but it is still super interesting. And it's based on something called a rearrangement. And it's too theoretical for this course. I feel it is, but it's really cool. So suppose that you have a series that is absolutely convergent. Now, we've just proven a theorem. If that series that you're handed, which might contain some negative terms in it, if it is absolutely convergent, then it's convergent. So we know that series is not only absolutely convergent, but it's convergent. And let's pretend as though the summation of that series is some value. We'll just call it S. Then, remember, if you sum up, let's just say we're summing from n equals 1 to infinity. That means that A1 plus A2 plus A3 plus ... onto infinity, if you add those up forever and ever and ever, that'll add up to S. And it doesn't matter how you add that up. So S is also equal to A3 plus A5 plus A2 plus A10 plus ... As long as I add each and every term along the way, that summation will still be S. And I think for all of us, that makes sense. If I added 3 billion numbers together, it doesn't matter how I add them because addition is commutative, that the sum will always be the same. But something your instructor should have made mention, I guess, with calculus is when you deal with infinities, a lot of our arithmetic logic falls apart. And here's where that specifically does fall apart. So that is true if you have an absolutely convergent series that no matter how you add up the terms, it will always end up being whatever that series converges to. But if you have a conditionally convergent series, so I'm looking at this second paragraph, if you have a conditionally convergent series, let's pretend as though, oops, I need my pen. Let's pretend as though S is equal to the summation n equals 1 to infinity of A sub n. Okay, so that is A1 plus A2 plus A3 plus so on and so forth. Okay. When you add it up that way, the way it's written, it will converge to some value of S, right? Just like we did up above. However, if it's conditionally convergent, then you can make that summation add to anything you want by rearranging it. Let R be any real number. Then R can be equal to, let's just say, A3 plus A7 plus A2 plus A10 plus blah, 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 blah. This is a really interesting result that conditionally convergent series, they converge to a very specific value if you add it up in the order handed to you. However, if you add it up in a different order, it'll become possibly something different. And for any given real number R, you can add up your series to match that. There are some exceptions. For example, if your conditionally convergent series, no, there is no, never mind. I was going to make an example, but that's actually absolutely convergent. So if it's conditionally convergent, you can create any number. Let's say that your series was supposed to add to 10. Let's just pretend. You can make it add up by rearranging it. You can make it add up to pi. That's just a trip, right? So that's why conditional convergence is a weaker form of convergence, because there are ways to add up those numbers. And this is where calculus is different from arithmetic. Arithmetic, if I add up 100 numbers, doesn't matter how I add them, it'll add to the same number. But calculus, you're adding to infinity. And because of that, there's strange things that happen. This dips our toes into really high-level theoretical mathematics. You can't actually prove that in this course. You need an analysis course, which is basically like near to graduate level course, but super interesting result. I just think this is cool. You're not going to use it, but I just like to include little cool things like this every once in a while because I think they're cool. So ponder that. If you said to somebody, hey, if I add 1/2 plus, well, it has to be conditionally convergent. You have to create a series of, okay. So you said, if I add 1 to negative 1/2, to positive 1/3, to negative 1/4, to positive 1/5, to negative 1/6, and so on and so forth, you're talking to somebody like that, and you say, let's suppose that adds up to 27. Now I'm going to move things around. It's the same numbers, but I'm going to move things around. I can make that add up to pi, or to 5, or to negative 10. It's the same set of numbers. It just, to a lot of people, that blows their mind. But the reason why it works is because you're adding to infinity. And so because that, you can add in any given order forever and ever. And it's such a cool little theorem. But we're not going to use it. And your author doesn't even have an example of it, honestly. So I could be wrong about that. Maybe he does. But anyhow, so now let's get into the meat of this section. Notice that was weird. Oh, I bet you, is my internet really terrible? Am I cutting out? Because it just turned off my recording, turned it back on. So I'm just curious if I'm cutting out a lot. You're not cutting out. Okay, thank you. All right, perfect. I just want to make sure because my internet has been terrible at certain points of the day for some random reason. Everybody working at home. We are now into the last two tests, and I spent about a half hour talking about the idea climbing up to this because these tests are super fast. There's no need for me to spend forever on these. The ratio test is probably my honest. So I've told you, like, the limit comparison test is a go-to test when it comes to comparison tests. The ratio test is my go-to when it comes to any test. The ratio test is my first reaction. I dive into the ratio test if there's something not obvious otherwise. So I will try the divergence test before the ratio test, but other than that, pretty much the ratio test is kind of my go-to. So let's talk about this. Given a series, summation A sub n, which could have some alternating terms in it, we're going to define L to be the limit as n goes to infinity of the ratio, that's why it's called the ratio test, of the next term in line to our current term. I like saying it that way. So I'm going to point an arrow and I'm going to say, this is the next term in line, and this is our current term. This actually seems a lot like limit comparison test to people. However, you're not creating a brand new sequence. You're actually using the same sequence. You're just looking at the next term in line and comparing it to the current term. Now, I'm not going to do the proof. The proof is in the textbook, and it's a little bit bulky, honestly. That's why I'm not going to do it. But I'm going to justify the proof with some just common sense. If the next term in line is always slightly bigger than the current term, so in absolute value, by the way. So let's go ahead and write that off to the side. If a sub n plus 1 is always slightly bigger than the current term, then what do you think is happening to the summation? If you keep adding terms of the series and each term is getting slightly bigger than the last one, what do you think the series is going to do? Yeah, the series is going to blow up. It's going to get bigger and bigger and bigger. It might go to infinity. It might just bounce between infinity and negative infinity because your terms might be alternating between positive and negative. But still, it gets bigger and bigger. You're absolutely right. It gets massive. So if that's the case, well, first of all, if that's the case, then we can easily say that a sub n plus 1 over a sub n is greater than 1. And by the way, that's an absolute value because that one of them could be negative. So we know that that fraction's bigger than 1, and that implies the series a sub n is likely to diverge. Likely diverges. It just blows up. I hope that makes sense to everybody. That's a really nice idea. If your terms are just getting bigger and bigger and bigger, then you're adding larger and larger and larger terms. As time goes on, your series will blow up. And if you take a look at, this bottom one right here, wait for it. If L, the limit, is greater than 1, that implies the series is divergent. Okay. What if the current term is always less than the next term in line? That is, the other way around. The current term is always greater than the next term in line. That is, the sequence is getting smaller and smaller and smaller as time goes on. It's basically a decreasing sequence. It's really what you're thinking about. Now, we've seen decreasing sequences where their series diverge. However, we're not talking about just the terms. We're talking about the absolute value of the terms. So if that's the case, then, and I should say an absolute value here, then let's see, 1 is greater than the absolute value of a sub n plus 1 over a sub n. That is, the absolute value of a sub n plus 1 over a sub n is less than 1. So if that ratio is less than 1, that means that as time goes on, our terms are getting smaller and smaller. We are adding less and less. And naturally, we tend to visualize that as a series converging because you're adding smaller and smaller numbers as time goes on. We do know that there are exceptions to this rule. For example, the summation of 1 over n, that will actually diverge. But for the most part, this is actually should make sense that this will tend to converge as time goes on. And that actually is true. If the limit is less than 1, this implies the series is absolutely convergent. Now, you might be thinking about the summation of 1 over n and going, wait a second, those terms are decreasing. But if you were to take the ratio of the n plus first term to the nth term and take that ratio as n goes to infinity, that limit is not less than 1. It's actually equal to 1. And that is this last piece right here. If you were to add those terms up forever and ever and ever, and the next term in line is roughly equal to the current term, that means that you're constantly adding roughly the same amount over and over again. So let's say the current term is 1/5, the next term is roughly 1/5. And as time goes on, you're roughly adding 1/5 on forever and ever and ever, and that could diverge. Or if you're adding 1/5, but the next one's slightly less, but not very much less, like when you're summing up 1 over n, that could converge, just depends. So if that ratio tends to 1, we can't say anything because we don't know how fast is it approaching 1. Is it approaching 1 quickly or is it approaching 1 slowly? We don't know. So given a series, alternating terms or not, you can compare the next term in line to the current term, take the absolute value, take that limit. If it becomes finite, actually it doesn't even have to become finite, honestly, but if that limit is less than 1 and is finite, that is true. If it's less than 1 and finite, that implies the series is absolutely convergent. If it's equal to 1, we can't say anything. We have to do another test. Inconclusive means do another test. And if that ratio is greater than 1, then the next term in line is always bigger than the current term. That series is going to blow up, and so it'll be divergent. The main thing that trips people up is when the limit is 1. So please remember, if that limit tends to 1, we have to switch to a different test. And that does happen actually quite often. We'll see it in examples. This is one of the easiest tests to use because notice there's no condition to use it. I hand you a series. Guess what you can do? You can use a ratio test. There's no like, oh, it has to be decreasing or it has to limit to 0. Nope. You can just use the ratio test. So that is why it's one of my favorite tests to use, because I don't have to sit here and go, can I use it? The answer is yes. So let's see it in action. It's a really neat series. So take a look at this horrible looking, or it's a really neat test. Take a look at this horrible looking series. Terrible looking series. Atrocious series. And if you think about all of your previous tests that you've learned, it's not geometric because not everything is to the nth power. So I'm just going to say not geometric. I suppose that you could possibly take, no, actually, I'm going to tell you right now, you can't do the integral test. You can't do the integral test because of the alternation here. Think about any time in your mathematical career, this semester or last semester is essentially your mathematical career in calculus. You've never been able to integrate -1 to the x power. You can't do that. There's just no way. So whenever you have an alternating term in there or an alternating factor, the integral test is out of the equation. Integral test. Nope, you can't do that. So looking through the other tests, I'm not going to write them all down, but those two are kind of the ones that I just quickly want to showcase. It's not neither of those. Think about the other tests. You have series comparison, limit comparison tests. Well, that's a lot of work to build something to compare this to. You could try the divergence test, and often really good choice. But in this case, this series is really busy, very, very busy. And with such a busy series like this, if I do the divergence test, it might not be the first thing that I do, just because this is really, really busy. So I'm going to go ahead and just try the ratio test because there's no condition to start using the ratio test. I could just use it. So let's try the ratio test. Super fun test because you're just going to take the limit as n goes to infinity of the absolute value of the next term in line over the current term. Now, the better way to say this is it's the limit as n goes to infinity of the absolute value of the next term in line times the reciprocal of the current term. Or maybe I should say of original sequence. It's just much cleaner to do that. So let's go ahead and try this out. That's equal to the limit as n is tending to infinity, the absolute value. Let's go ahead and take this sequence right here and replace those n's with n plus 1s. So I will have a negative 10 to the n plus first power. Downstairs, I'll have 4 raised to 2 times n plus 1 and then plus 1. That'll be 2n plus 3. I'll have an n plus 1 here, so that's an n plus 2. And I'm going to multiply that by the reciprocal of the original sequence, which is just 4 to the 2n plus 1 times n plus 1 over negative 10 to the nth. Now, the negatives don't matter. You're taking an absolute value. So you can erase those negatives. In fact, that's what I'm going to do. I'm just going to erase the negative there and the negative there. No need to have those because you're going to take the absolute value. Now let's clean this up. 10 to the nth, that goes into this 10 to the nth, and I'm still left with 10 to the first. I'll move that 10 to the first outside of the limit, so that I still have a 4 to the 2n plus 1 times n plus 1 divided by 4 to the 2n plus 3 times n plus 2. Now you can cancel those using laws of exponents, the 4 to the 2n plus 1 and the 4n to the 2n plus 3, 4 to the 2n plus 3. That will leave me with a 4 squared in the denominator. So I'm going to move a 4 squared out front. Whoops. And as n goes to 4 to the 2n plus 2. No. So it's being asked, wouldn't it be 4 to the 2n plus 2? No, when you plug in n plus 1 into that, remember, you're still adding 1 at the end. So it'd be 2n plus 3. Yeah. And taking a look at this limit, the limit as n goes to infinity of n plus 1 over n plus 2 is 1. And so this is going to be 10 over 16. Sorry, I was going to say 10 over 6. It's 10 over 16. Now, remember what our theorem said. If this ratio, the limit as n goes to infinity of the absolute value, if that's less than 1, then our terms are getting smaller and smaller and smaller and smaller, which means our series converges absolutely. This implies original series, that's what I'll just write, rather than copying the original series. The original series converges absolutely. Which, by the way, not only does that mean the absolute value of all the terms when you add them up, it converges, but it also means the original series just converges. So when I say converges absolutely, I'm going to put in parentheses here, implies original series converges. You don't have to do that. When you tell me the original series converges absolutely, it implies anyway, just by saying those words, that the original series converges. But I'm just reinforcing that idea here. Look how nice that test is. Super duper nice. Like, that's the test you want to use. And by the way, for those of you who are moving into differential equations, which I highly recommend that you take that after you take Calc 2 rather than waiting, you're going to be using the ratio test quite often. So getting to know this test is very important. I'll pause for a moment if you have questions. Oh, there is a question. Okay. So what if a series diverges and its absolute value series converges or diverges? So the question is it possible for an example, this series to diverge, but its absolute value to converge? Nope, not possible. It's totally not possible for a series to diverge, but its absolute value converges. Remember, if the absolute value of the terms of a series converge, let me hop back a few pages here. Where are we? Right here. Remember, if the absolute value of the terms of the series, when you add them up, if those converge, that will immediately imply the original series, no matter what it looked like, will converge, period. So if so you will never have a case where a series diverges, but its absolute value will converge. That's just not going to happen. You can have a series diverge where you could. Maybe I'll write this down off to the right. It can be the case. So I want to make this very, very precise. So if the summation absolute value converges, then it has to be the case by our theorem here that the original series converges. If the absolute value of a series diverges, then the original series could still converge. That is the case. Like, just because the absolute value of a series diverges does not say anything about the original series. The original series you still have to test. Okay. If the original series converges, if a series diverges, maybe I should read. If the original series diverges, then there is no way for the absolute value of the series to converge. It's just not going to happen. So if the original series diverges, then the absolute value of the series will diverge. Because let's just pretend for a moment that you said, oh, this original series diverges, but the absolute value converges. Well, remember, if the absolute value converges, then the original series has to converge as well. So there's no way for the original series to diverge, but the absolute value to converge. And then let's see. So let's convert. Let's do the last one. If the original series converges, it could be the case. Then the absolute value could still converge or diverge. We just don't know. So notice, yeah, there's not a great pattern there. But yeah, just know that absolute convergence implies convergence. That's the easiest way to say it. Absolute convergence implies convergence. This guy right here. The contrapositive is always true. So if the series diverges, then the absolute value will diverge. That's this second statement here. If the series diverges, then the absolute value will diverge. There's no way for it to converge. So that's the contrapositive. Remember, every theorem that you're given has a contrapositive. That's also true. But those other two, which I'll circle, I'll put red X's by, those other two are ambiguous. Okay. I know that sounds confusing. It's because you're first learning it. It's totally confusing. I probably would not even memorize that list of 4 things. I would just stick with this statement. And then I would say, if it's any other case, I'm going to have to think about it. That's probably the best way to do it. Just say, I'm only going to memorize this. I have an absolutely convergent sequence or series, sorry. Then I know the original series is convergent. Everything else is off the table for now. Okay. I don't know if I overly confused it. I apologize, Veronica, if I made that worse. All right. So let's try another example. And this might help you out kind of with what I tried to explain there. Determine if the following series is absolutely convergent, which means conditionally convergent. I should have written that. absolutely convergent, conditionally convergent, or divergent. Well, here's the deal. If you take a look at the terms of this series, they're always positive. So if this converges, it's absolutely convergent because, well, it's always positive. There are a lot of ways you could possibly go about this, I suppose. I'm trying to think of probably the easiest way, or not the easiest. The easiest is the ratio test, but I'm trying to think of another way. You might be able to showcase this diverges using, nope. No, I was going to say using divergence test, but it's actually convergent. So yeah, if you look through all the tests that you have prior to today, I'm guessing probably the one that most people are going to go for this is a comparison test. To make a little note here, you again have never dealt with the integral of x factorial over 5 to the x dx. This x factorial, that doesn't even make sense when you have a continuous variable x. So anytime you see a factorial, integral test is out. So these are little lessons that you learn as you move through move through calculus. But little note here: integral test is useless if given a series where you have a negative number to the nth power, or a series that has some n factorial or something like that. So integral test is just junk for those. You can't do that. I know we're not talking about the integral test specifically here, but that's just good to note. Okay. So again, for me, I take a look at this and I think, I'm just going to go ahead and dive right into the ratio test. Whenever I see a factorial, ratio test is almost screaming to be used. Remember that we were dealing earlier with like n to the nth over n factorial and stuff like that? And we had to expand that out with the multiplication. Now you don't. The ratio test is pretty much the most ideal test to use when you have factorials, because you're going to take the limit as n goes to infinity of the absolute value of the next term in line times the ratio, or times the reciprocal of the current term. Well, let's see, the next term in line, and because everything's positive, I'm just going to remove the absolute values. The next term in line is me replacing these n's with n plus 1s. So I have an n plus 1 factorial over 5 to the n plus 1. Multiply that by the reciprocal of the current term. So the reciprocal of this stuff, it's 5 to the nth over n factorial. Notice I didn't bother with absolute values because these terms are never negative. So I don't have to worry about the absolute value. Well, we know that 5 to the nth and this 5 to the nth will cancel, and we'll have a 1/5 outside of the limit. And we have an n plus 1 factorial over an n factorial. That will simplify down. Remember, n plus 1 factorial is n plus 1 times n factorial. It's n plus 1 times n minus 1 times n minus 2, so on and so forth. So the n factorials will cancel. You'll have 1/5 times the limit as n goes to infinity of n plus 1. And that tends to infinity. Now remember, what we're basically saying here is that the ratio, as time goes on, the next term in line is infinitely larger than the current term. This thing's going to blow up. This thing blows up quickly, in fact. So this is greater than 1. This tells me that the original series diverges by the ratio test. Again, when the next term in line is getting larger than the current term, your series is just going to blow up. That's kind of the easiest one to visualize. When the next term just keeps getting bigger and bigger and bigger, you're adding up larger and larger numbers, so it's going to blow up. So again, very nice. Notice how it's built. Really, the ratio test is built for factorials. Super awesome. Questions on that? And I'll pop forward. I'll hop back if I can answer a question. So let's see here. Yet another example. Determine if the following series is absolutely convergent, conditionally convergent, or divergent. And it's being asked, I'm confused as to how the original series is divergent. So it's the original series divergent because of the ratio test, right? The ratio test tells us if we take that limit as n goes to infinity of the next term in line to the current term, and if that limit ends up being greater than 1, the series is divergent. It basically means that you're adding numbers. So here's your series. It doesn't really matter to me what your, well, let's look at the absolute value. Well, let's look at the original series. Let's say that you have some original series, you've added up a bunch of terms, but as you're adding them up forever and ever and ever, it's something like, let's just say 8/9 minus 9/9 plus 10/9 minus 11/9 plus 12/9 minus 13/9 plus 14/9, and so on and so forth. Do you see these terms in absolute value are getting larger and larger and larger and larger? And so because of that, this sum will actually wiggle away from 0. This will get larger and larger and larger as time goes on. Yeah. Okay. So here we are. So determine if the following series is absolutely convergent, conditionally convergent, or just divergent. Now, we haven't seen a conditional convergence. We will. I have an example of it, but let's just go ahead and just dive into the ratio test right here. So let's take the limit. I'll write down ratio test to let the world know that I'm actually using it. But we'll take the limit as n goes to infinity of the absolute value, which, by the way, there's no need for absolute values again, because both the numerator and denominator are actually positive in this situation. So again, not a big deal, but let's go ahead and leave them on there for now. We'll look at the n plus first term. If you let this n be n plus 1, you'll have 2 times n, which is 2n, plus 2 minus 1 times, and then the reciprocal of the original sequence, which is a 2n minus 1 factorial over n squared. So really a very, very pretty example. Let's go ahead and see what this tends to. That's the limit as n goes to infinity. Let's see. 2n plus 1 factorial. Let me write this in blue ink for you. 2n plus 1 factorial is a 2n plus 1 times a 2n plus 0 times a 2n minus 1 times a 2n minus 2, times a 2n minus 3 times a 2n minus 4 times a 2n, basically 2n minus 1 factorial. So you can see what will cancel between numerator and denominator there. So we have something like this. You could technically multiply out that numerator if you want to, because you know what's going to happen, but let's just go ahead and do it. N squared plus 2n plus 1 in the numerator. Downstairs, you have n squared times 2n plus 1 times 2n. And if you divide top and bottom by n squared, let's just do that. You'll get 1 plus 2 over n plus 1 over n squared. So the numerator will tend to 1. And the denominator, when you divide that by n squared, you get this. Numerator is tending to 1, denominator is tending to infinity, and so therefore this tends to 0. Now, I like this example because if you were using the limit comparison test, it starts getting confusing. But if you use the limit comparison test, which we're not here, we're using the ratio test. But remember, the limit comparison test says that if the ratio is strictly positive and finite, then the series will converge or diverge together. The ratio test does not have a quibble like that. It just says, hey, if your ratio, when you can do the ratio test, if the value is just less than 1, it could be 0. That's totally fine. Then we know that your series will converge absolutely. So it's okay that this limit turns into 0. So this implies series converges absolutely. So a significant difference between the limit comparison test and the ratio test. Limit comparison test, just to showcase this by fast forwarding slightly. The limit comparison test, waiting for this to, there we go, requires us to compare our given series to a different, or sequence, to a different sequence. The ratio of that, as you take n going to infinity, we want that to be a finite and positive number. That's the limit comparison test. The ratio test just says, did I just copy that? Whoops. Oops, I wrote them backwards. So I'll have to clean up that. I have all my divergence stuff up above, but I did the convergence for the ratio test up here. So I'll clean that up in my lecture notes. But anyway, the ratio test tells us that if the ratio is less than 1, it could be 0, then we get absolute convergence. I didn't realize that I had that backwards on there. The last one we have here is a lesson in when our ratio test is not usable. So determine if the following series is absolutely convergent, conditionally convergent, or divergent. If you take a look at this summation, it does have some alternations in there. Now, if this was on an exam and they said determine if it's absolute convergent, conditionally convergent, or divergent, I would probably still do the ratio test because the absolute convergence is part of the question. And yeah, so let's go ahead and just use the ratio test, or try to use the ratio test. How's that? To see how this works. The limit as n tends to infinity of the absolute value of the n plus first term. Now, again, there's no need for me to write the -1 because we're taking absolute values, but I'm just writing it in there for your benefit so that you know I'm putting n plus 1 into this sequence. But the reality is the -1 will disappear when we take the absolute value. So there's no real need to write that in there. And multiply that by the reciprocal of the original sequence. And again, I'm just going to erase the negatives because there's no need to have the negatives in there. And you can see that this is just the limit as n tends to infinity of n squared plus 1 over, it's supposed to be an n, not a negative n, over, well, I'll multiply this out, why not? N squared plus 2n plus 2. And as n goes to infinity, that's going to be 1. And one thing that we know is that this, the ratio test tells us that if the limit of the ratio of the next term in line to the current term is 1, we cannot use the ratio test. The ratio test is inconclusive. It's inconclusive because we're saying the next term is roughly the same size as the current term. Well, if the next term is 20, then the current term, or I'm sorry, if the current term is 20, this means the next term is 20, and the following term is 20, and the following term is 20, and we're adding up a bunch of 20s. Or if the current term is 0, the next term is 0, the next term is 0, the next term is 0, so we're adding up a bunch of zeros. In the first case I mentioned, it would diverge, the series would. In the second case I mentioned, these series would converge. So because the ratios are equivalent, in other words, next term in line is basically the same as the current term, that means that we have to switch to a different test. So this implies switch to a different test. So we're going to go ahead and switch to a different test. There's nothing we could do here with the ratio test. And by the way, we still have to answer, is it absolutely convergent, conditionally convergent, or divergent? So if I want to showcase it's absolutely convergent, which is usually the first thing you want to do, you'll go ahead and worry about the absolute value of the sequence term. So let me go ahead and say, let's look at the series 1 over n squared plus 1. Right? There's no other way to do this problem. We're starting at 0, by the way, because I want to showcase, we can easily see that this is going to converge, but we have to actually prove it will converge. We can't say that it's a p-series test because it's not. It's a 1 over n squared plus 1. It's not a 1 over n squared. So you can't say it converges by p-series test. I do know it converges. Don't get me wrong, but just not by the p-series test. So to showcase that this converges, and if it does, it converges absolutely because we've just taken the absolute value of our original sequence terms or series terms. To showcase that this converges, let's try maybe a series comparison test. Well, let's see. N squared plus 1, that's greater than n squared. And therefore, 1 over n squared plus 1 is less than 1 over n squared. Yay. Oh, by the way, that's positive. So that's a great comparison. Series comparison test will work here. So, and the summation 1 over n squared converges. That's the p series test. So I was able to actually use that elusive p series test. You could also do this with a comparison test, a limit comparison test. But since we know, oops, wrong one. Since we know the summation of this sequence converges, then we know the summation of this sequence converges by the series comparison test. So this implies the summation 1 over n squared plus 1 converges by series comparison test, or you could have used a limit comparison test. Totally could have. Which implies, by the way, that the summation -1 to the nth, it's our original series, yeah, over n squared plus 1 is absolutely convergent. Once you showcase that it's absolutely convergent, it converges, period. So showing absolute convergence is a wonderful umbrella statement. If you can show something absolutely converges, you've killed 2 birds with 1 stone, essentially. Really, really good example of when a ratio test goes wrong. And as my note here says, which I should have the word note in there, so I have a little cleanup on these notes. The note here says rational expressions involving polynomials or radicals over polynomials are always bad for the ratio test. You could try them, but they just will always limit to 1. And so they'll always be inconclusive for the ratio test. You don't have to memorize that because it only took a moment for me to figure out it was inconclusive and I had to switch to a different test. But it is helpful in the long run just to know when you can and cannot use the ratio test. That's a really good example. I like that example a lot. All right. What about that other test? You may say, but wait, we only have 11 minutes. How are we going to learn another test? The other test is just like this test. Super nice. The other test is called the root test. And the root test is going to be usable, really usable, if you have an nth power on your series. So that is, it looks geometric. If it looks geometric, it has an nth power on everything, then the root test, which allows us to take the nth root of our sequence terms, is super duper awesome. What we're going to do is take the limit as n goes to infinity of the nth root of the absolute value of the nth term. That's a lot to say, but basically just take the nth root, right? Take the nth root to power down your sequence terms, let n go to infinity. If that ends up being greater than 1, then your series will blow up because your terms are getting larger and larger, basically. Okay, so if that ends up being greater than 1, the series is divergent. Because again, think about a number greater than 1, and you're taking the 1,000th root of it. The 1,000th root of a number greater than 1 is still greater than 1. And so as time goes on, you're adding numbers greater than 1 over and over again. So your series will diverge. If, on the other hand, this nth root, as n goes to infinity, ends up being less than 1, that will imply that your series will converge. And that is because you're taking the nth power. Remember, you're really using this on a series like this. You're taking the nth power of something less than 1. Now think about that. Take the 100th power of 1/2. That is basically sucked down to 0 very quickly. And so you're adding essentially zeros very quickly. So our limit being less than 1 implies that we have absolute convergence, that our series will converge. Because we're dealing with the absolute value of our sequence terms, it's absolutely convergent. And just like the root test, if that limit is 1, this implies nothing. We have to switch gears. It's a really easy test to use, so let's just see it in action. It's actually pretty entertaining. Here's a series. Determine if it's absolutely convergent, conditionally convergent, or divergent. Well, if you take a look at that, you might say, that doesn't look like it has the nth power on a sequence term, but it does. That is the nth power of something. How do I know? Because I know the laws of exponents, and so do you. You know that this can be rewritten as n to the nth over 3 to the first times 3 to the 2n. I can factor out 1/3. And so this third has been moved out front. And 3 to the 2 to the n, this guy right here, is actually 9 to the nth. It's 3 squared to the n. So believe it or not, that is a sum of a bunch of terms raised to the nth power. Those terms are n over 9. Now, you may say, can I use the geometric series test? Let me give you a big fat warning here. No, you cannot use geometric series on this one because it's not a geometric series. To be a geometric series, that common ratio inside has to be constant. It has to be a 1/9, not an n over 9. It has to be like a 1/9 or an 8/9 or a 57/9. I don't really care what it is, but the reality is it cannot be an n over 9. So it's not geometric, even though it looks geometric, totally not geometric. So I cannot resort to using a geometric series here. However, I just learned a brand new test called the root test, which means that if I want to determine if that series converges or diverges, I could just take the nth root of its sequence. So let me go ahead and write ratio test. I'll take the limit as n goes to infinity of the nth root of the absolute value of the sequence, which is n over 9 to the nth power. The 1/3 is not going to, by the way, hurt. Oh, it's a root test. Thank you. Sorry, brain. So the 1/3 is not going to hurt convergence or divergence. So don't worry about the 1/3 hanging out front. All right, let's go ahead and make a couple mentions here. One thing to mention is that n over 9 is always positive because n's going to infinity. So I don't need the absolute values. However, I could move the absolute values on the outside if I wanted to, but there's no real need to do that here. Okay. So the other thing to note is the nth root of the nth power, just like the square root of x squared, that will always return the absolute value of the argument. And so this will be the limit as n goes to infinity. So basically I have a double absolute value going on here. Nth root of something to the nth power is always the absolute value of that. However, again, n is just positive. So if n is positive, I can remove those absolute values. And notice what this tends to. Something greater than 1. That's all I care about. Something greater than 1, which means by the root test, not the ratio test, sorry about that. By the root test, this original series is divergent. Because the the limit is greater than 1. So really a very nice test to use. Now, I'm going to pause it here. I want to talk about a couple things before we end. So it's a good time to pause anyway, because then on Wednesday, when we pick back up, we have one more example to reinforce this idea, and that's all we have. And then we'll go into newer material. But we do have a quiz today. The quiz is on, give me a moment while I look, 11.3. It is a single question quiz, and you'll have 10 minutes. And it does require an upload. So it's a 10-minute single question quiz. So that's one thing to mention. The other thing I want to mention is that I'm modifying slightly a couple things in my lectures so that we really spend our time in class on the targeted information that's super important. So coming up in section 11.8, maybe, there'll be little minor things that I'll have pre-recorded videos for, just like an example or two, because they might just be extended examples or something like that. So I'll let you know, like, oh, there's 2 more examples online in the section, the homework section, that you can view if you need extra examples, or it might be a proof of something or whatever it may be. That's mainly to gain us a little bit of time. We don't need to actually gain a lot of time, but just in case, I'd like to make sure that we have that cushion at the end of the course, so that I'm not running us into the very last day lecturing. The last week should not have a single lecture in it. The other thing I should mention here is that I will, while everything in this test so far statement right here is true, turns out that I parked these in the wrong spot. So these should go down to the convergence area, and these right here should go up to the divergence area. So I'll swap those. But otherwise, everything is pretty clean. Those are all the tests that we have learned and will learn for the convergence or divergence of series, infinite series. So pretty good stuff. I don't think there's anything else that I need to mention. The schedules online for the fall are out and should be cleaned up at this point. I'm teaching 401 and 410 in the fall. I'll be teaching online just like this. However, what I'm going to do in 410 is slightly different. I'm going to put some prerequisite videos up because 410 has a lot of prerequisite information. So those will be up, and then lecture will be less hectic. It'll be more open for Q&A because that type of class requires a lot of back and forth. So this is 410 is linear algebra. It's just being asked. So if you have to take linear algebra, I am teaching it online in the fall. So you can look online on the schedule, but the setup of the course is similar, but not exactly like this. There'll be a lot more back and forth because that course, you need it. You need to hear people talking. You need to hear the questions. It is just like when you went from pre-calculus to calculus, there was a shift in mindset. There's another massive shift in mindset when you go to linear algebra. That's a very theoretical course, lots of proofs, although easier proofs than what you may think, but still a massive shift in mindset. Anyhow, keeping you too long. You guys have a wonderful day. I'll be back here in 9 minutes. And as far as uploading, I'll see if I can. I'll stop this recording. That's a major issue. If I don't stop the recording, let me stop this recording. Then